If you think back to how we found the derivatives of the inverse trig functions, the a lot of that process would work for any invertible function. Everything except the calculation at the end where we drew a picture with a right triangle. That was the only part that had something to do with trig functions in particular. So if we had any old function that is defined on some interval and has an inverse, we might wonder if we can if we might wonder that if we know if the original function is differentiable, is the inverse function differentiable? So suppose we know that f of a is b. So suppose we have a particular x value on the original function with a corresponding output b. If we know that the function is differentiable at this point, that means we know that it has a good tangent line, right, like this. So what does this tell us about the inverse function? Well, if f of a is b, then another way to express the same idea is that f inverse of b is a. Remember that inverse functions just switch inputs and outputs. So if f of a is b, then f inverse of b is a. And that means that there's a corresponding point on the graph of the inverse function. So it would have b as the x-coordinate and a as the y-coordinate, like this. And remember that sort of another way to, maybe I could make this a little bit better. I think I put my b a little bit too far to the right, maybe more like this. Okay, now it looks a little bit better. Something that we know about inverse functions is that the graph of the original function and the graph of the inverse function look the same, except that they've been reflected over the line y equals x, which looks like this. Well, and you can see that here because this point, a comma b, on the graph of the original function gets reflected down to the point b comma a on the graph of the inverse function. But we could also graph this tangent line. If we graph this tangent line, then it sort of gets reflected onto a tangent line for the inverse function, but not at a, over at b instead. So what does that tell us about slopes? Well, the slope, let's express the slope of the tangent line on the original function. So this would be f prime of a. And we could measure that slope by moving over a little bit and up a little bit. Right? If we called the distance we went over maybe p, and the distance we went up q, then that means f prime of a is q over p. But when we reflect this all down to across the line y equals x to get the graph of the inverse function, these line segments p and q also get reflected. But since we're reflecting over this diagonal line, p, which starts out horizontal, actually ends up vertical. And q, which starts out vertical, ends up horizontal, like this. So, reasoning from this picture, not only does the inverse function have a derivative, let me write it like this, not only does the inverse function have a nice derivative at b, but we can actually write down what it is. It's just the slope of this line, which is p over q. But look, that's just the reciprocal of the derivative of f. But not the derivative of f at b. We don't know what the derivative of f at b is. That would be up here somewhere. It's actually the reciprocal of the derivative of f at a. So it seems like if the inverse function is differentiable, then its derivative has to be the reciprocal, the derivative at b has to be the reciprocal of the derivative of f at a. Now, in fact, it is possible to prove that if the derivative at a exists and the inverse exists, then the derivative of the inverse function exists. But actually proving that, precisely is surprisingly technical, and so I'm going to not prove it. I think this diagram gives you a very good feel for why it has to be true, just based on the graph. But actually getting into the details of the proof sort of requires delicately thinking about one-to-oneness and exactly what goes on near these points. But the picture makes it pretty clear why it more or less has to be true, or at least why it's plausible that the function being differentiable would make the inverse function also be differentiable. All right, as long as the derivative of the original function isn't 0, right? If this denominator came out to be 0, then all bets would be off as far as the derivative of the inverse function. So this is sort of some nice geometric reasoning for why the derivative of the inverse function ought to be the reciprocal of the derivative of the original function. But we could also use the same kind of tricks that we used to find derivatives of the inverse trig functions. So let's find a general expression for the derivative of f inverse of x. So first of all, let's name this function. We'll name it y. And now we can apply the function f to both sides. On the left-hand side, we just get f of y. On the right-hand side, we f of f inverse of x. That's just x. We're trying to find the derivative with respect to x, so let's take a derivative with respect to x here. On the right-hand side, we get 1. On the left-hand side, we have to do the chain rule because the outside function is f and the inside function is y. Remember, y is really a function of x here. So we get derivative of f at y times the derivative of y, so dy dx. Now we can solve for dy dx. We get dy dx is 1 over f prime of y. Okay, and remember that y is actually f inverse of x, so this is 1 over the derivative of f at f inverse of x. Okay. And y was f inverse of x. So we found a derivative of f inverse of x. It's 1 over f prime, but evaluated at f inverse of x. This actually matches what we got graphically speaking, because if we called x a, then y is what we called b before. So this right here is actually b. So this formula that we got working sort of symbolically does match the formula that we got working geometrically.